Hey guys, welcome back. Day 16. We're going to talk about what I think is one of the hardest parts of chemistry, and that is the naming. All right. In most textbooks, for whatever reason, go into Lewis dot symbols, and we're going to naming molecular compounds, ionic compounds, acids, and then a little bit of organic compounds. Just very simple ones. All right. And so the reason this is hard because it's not math based. A lot of people who come into STEM think a lot of math, but this is more language based. All right. And so this, if you're a language person, fantastic, right? You'll enjoy this. If you're not, well, this is a big fundamental, right? This is like the foundation, okay? And when we talk about naming in general is like very systematic, because when we name things, we name them in a way. I didn't do this. This happened years before me. I can't take credit for it. But we name them in a way that helps us predict the behavior of the compound or know its chemical properties, right? That's very important. There's two big distinctions, right? The ionic and the molecular, because they're put together differently. And we're going to dive all into that. But first, let's dive into these Lewis dot symbols. Guy by the name of Lewis. If you've had chemistry before, you've done Lewis structures. Same guy, all right? Fantastic contribution to the field. All right, so he uses dots. Lewis uses dots to represent, right, a valence electron. So the dot is a valence electron, okay? All right, and so hydrogen would have a dot. Helium would have two dots. Now, sometimes you would see helium and two dots like that. Why would I do that? Well, because, that's a highlighter. Because we have 1s2, right? And it's full. 1s2 is full. All right. Technically speaking, a lot of times you'll see it where you have the element and they'll go around, 1, then 2, 3, 4, 5, 6, 7, 8. But it doesn't really matter. The key thing is that there's only 2 electrons on the sides. Does that make sense? Hopefully, if you make like a box around the X, the element, there's only 2 per side. That's the big thing. All right, so lithium, dot. You're good. Beryllium, 2 dots. Now, if you write beryllium this way, I'm happy. If you write it this way, I'd be happy in Chem 1, okay? Doesn't matter to me, because when S2 is full, I'm okay either way. We'll probably do the middle one, because if you do compounds with beryllium and you do Lewis dots with it, that's what it's going to look like, but I digress. Boron, 3 dots. Carbon, 4 dots. Nitrogen, most of the time the dots will look like that. Oxygen, most of the time will look like that. Fluorine, most of the time will look like that. And neon, of course, has all 8. All right. And now the thing is, you guys know that this is group 1, group 2, 13, 14, 15, 16, 17, 18. That's the group. And everything in the group ends in the same electron configuration, so they all have the same dot structures. Hopefully that makes sense, right? So nitrogen, 5 dots. Phosphorus, 5 dots. Arsenic, 5 dots, all right, as you go down. And the reason the 2 dots are on top of like nitrogen here, right? The reason for this is because nitrogen makes 3 bonds that we'll learn, and there's 2 dots on the top of what we call a trigonal pyramid. And so that's why it's that way. Does it matter? If you were to do nitrogen, if you did nitrogen and you had 2, 3, 4, 5, you did it that way. Is that wrong? Absolutely not. That's perfect. Okay? That is perfect. I'm happy with that. No issues. Okay? So Lewis dots, pretty straightforward, and we introduce them in this chapter, but we don't do them for the next couple chapters, which is fine. All right, so now we're going to dive into naming. All right? Okay? And first, we got the formulas. And there are 3 formulas, right? There is the molecular formula. And so a molecular formula here is C6H6. That's your molecular formula. Okay, that's the formula of the molecule. There's 6 carbons, 6 hydrogens bonded together. Okay, it doesn't tell you how they're bonded together. It just tells you that they are bonded together. Okay, and that's what we use to get the molar mass. All right, so this is molar mass or formula mass, formula weight, right? Balancing equations. Right, calculations. We use that the most. All right. Then there is the structural formula, right? And this shows how they're put together, all right? As you can see, they show you how the H's and the C's and how many bonds, right? That's the structural formula. That's very important later on. Now, we're not there yet. We're not doing that yet, right? And so that's okay, but that's how it's done, all right? And then there's the empirical formula. That's the empirical formula, which is the lowest ratio, the simplest ratio, okay? All right? All right? And that is important. Now, what's really important is that all ionic compounds are written as empirical formulas. All right? That's very important, okay? That means we can reduce empirical formulas, right? What do I mean by that? NaCl, basic ionic compound. Is Na10Cl10 wrong? Absolutely not. That's the right ratio. It looks weird because it is. All right. Okay, we're not going to do that. You always reduce to NaCl for ionic compounds. However, you can't do that here. Okay, you can't do that because sometimes molecules will have the same empirical formula. Right? Benzene has the same empirical formula as acetylene, which is used in welding, right? If you use acetylene torch, not the same compound, totally different properties. So we can't do that with molecules because molecules are small, discrete units built together, all right? Okay, all right, and let's just dive into the molecules right now, right? A molecule is a particle composed of 2 or more atoms chemically bonded. It's a small, discrete unit of atoms, right? Small, discrete unit of atoms. If the atoms are the same, it's an element. For example, you have the oxygen atom. We have the O atom here, right? This is oxygen gas. Use a different color. And O3 is ozone. And ozone is a different allotrope of oxygen. So it's another elemental oxygen. It's just not the common one, right? But you've heard of the ozone layer, I'm sure. Big deal when I was a kid. Now, if the atoms are different, the molecule's a compound. And they're different compounds, all right? Okay. Now, N2O, this one is nitrous oxide. Common name. Nitrogen monoxide. And nitrogen dioxide. So we have to name them different because N2O, nitrous oxide, laughing gas. NO2, toxic gas. So you can't just say nitrogen oxygen, there has to be a naming system for this, all right? And what is that naming system? All right. Okay. We write the name of the element to the lower left first. So down here is first. And then last up there, changing it to "ide." Now, technically speaking, there is something called the IUPAC, International Union of Pure and Applied Chemistry. And technically speaking, we're going to write down carbon first, then nitrogen. All right, no, not nitrogen, phosphorus first. Phosphorus, then nitrogen, then hydrogen, and sulfur, iodide, bromine, chlorine, oxygen, fluorine. So that's the order, okay? If you get them out of order a little bit, it's not the end of the world. Okay, don't memorize and stress about this order. But that's the order. Okay, that's the order. Now, how many each atom? And I kind of did it up top with the nitrogen monoxide and nitrogen dioxide, right? We use prefixes here, right? Okay, mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hex is 6, hepta is 7, octa 8, nona 9, different language, and deca is 10. And I think you've heard of most of these. You heard of mono. You've heard of dice, 2 dice, right? Heard of triangle, tripod. Tetris was a big game when I was a kid in the original Nintendo. Penta, all right, pentagon. Actually, a lot of people, I've had many students where I get to work here with the military have gone to the Pentagon. Hexagon. Hepta is weird. We don't use 7-sided things much, hepta. Octagon. Every stop sign you see is an octagon, right? Nona is, again, different. Deca, decade. All right, so a lot of these you've heard before. We just now put them down for the compounds here. Now, when there's an A and an O together, we can omit those. All right, so we don't write, like I did here, nitrogen monoxide. You don't say nitrogen monoxide, you say nitrogen monoxide. Not a big deal if you don't do it, okay? All right, now, in general, the number of hydrogen atoms is not denoted by a prefix. Also that the prefix mono is dropped for the first element. Right, because if I say carbon, you know carbon's there. You obviously know. If I say dicarbon, you know there's 2 carbon. But if I say carbon, there's 1 carbon. Just like if you say x plus 3y. You don't say 1x plus 3y. I mean, you could. It's not wrong if you do. But you say x plus 3y equals 6. All right? So the same thing here. You would use the prefixes. And then you drop the mono because we don't need to say it. All right? And so if we look at some of these, you have CO2, which is carbon. There's the dioxide. N2, dinitrogen, 4 O's, tetraoxide. Now, technically speaking, you would drop that A, okay? If you don't, I'm just going to highlight it because that's an A you can drop. If you don't drop it, am I going to be mad at you? Absolutely not. So let's talk about that. Let's talk about the spelling, right? How important is the spelling? Well, what's really important? The A is not important, okay? The di is important. If I can tell the compound, the ending's very important, right? If I can tell the prefix and the element, right? So there's a couple things I need to know. But in phosphorus, if you put, instead of the pH, you put an F there, I mean, ideally you want to get to the point where your attention to detail is accurate, right? We want to get to the point where we are doing excellent work. However, as we're learning, it's not the end of the world if you spell phosphorus wrong. However, if you spell penta wrong, right, and you spell it as a different prefix, that's a big deal. All right, so we continue with these. You got oxygen difluoride, sulfur, 1 sulfur, tetra, 4 is tetrachloride, 1 phosphorus, so phosphorus, 5 penta, and then Cl is chloride. Now, hydrogen, here's 1. Hydrogen sulfide. You might say, well, there's no prefix there. You would be accurate. Okay. If you wrote dihydrogen monosulfide down, would I mark you wrong? I would not mark you wrong. Okay? Because you successfully communicated to me what the compound is. All right? You can, I guess it's maybe being lazy, or I don't know, but it's less writing. Because if you looked at the Lewis structures, and if you've done this before, if you've done chemistry before, you notice S has 6 valence electrons. It wants 8. We'll get to where it wants 8, and each hydrogen comes in, There's 2 bonding opportunities. It's H2S. And so if you know group 16, right, and you do this, if you actually do chemistry, you'll know it's H2S. It's always going to be H2S. If it's not H2S, I need to know. Otherwise, it's H2S. As you're learning, if you write out the dihydrogen monosulfide, I'm not going to be mad at you. Okay, just know that it's not going to be given to you that way, if that makes sense. You're going to be given hydrogen sulfide, and yes, you will expect to know it's H2S. If you write that down, though, not a big deal. Then you have nitrogen triiodide. Of course, there are some compounds that have special or common names. Like water was around way before, the field of chemistry was. So you got water, you got ammonia, methane, phosphine, right? Those are not IUPAC names. Okay. And there's also special names for acids and bases and organic compounds, which some of them will address in this video and some of them we'll address later. Okay. So that's the molecules. And the prefixes just tell us how many, right? Because they are small, discrete units of atoms bonded together. Right? And we need to know how many of each atom, right? Okay, for example, CO, carbon monoxide. All right? You can't just say there's a bunch of C bonded to O in the room. Okay? Because there's a bunch of C bonded to O in the room, well, that might be great, especially for growing plants. All right? Might not be a big deal, right? We're breathing it out right now. Okay? That's fine. But you've got to be very careful about the levels of carbon monoxide in the room, right? Obviously that you can have too much carbon dioxide, but we're not even close to that in most of this place, right? You guys might have a house, and you might have a carbon monoxide detector. We don't have a CO2 detector, all right? We have a CO detector, and so that's very important to know how many of each atom are there, because that's how these small discrete units are bonded, and their properties depend on that. The next class of compound are ionic compounds, right? And ionic compounds, they don't make a small discrete unit. They make a repeating lattice. Of cations and anions, right? They make a repeating, so it's positive, negative, positive, negative, positive, negative, right? But then it goes negative, positive here, negative there, right? And this happens in 3 dimensions. All right? And so it's just this ratio of cations to anions, these monatomic ions, like sodium is plus, cation, right? And most metals are positive ions. And then the nonmetals on the right side are negative, right? Tend to be negative, they're anions. So you have these positive and negatives in this array, this repeating pattern to the end of the sample. So that's why they're empirical formulas and not like actually have numbers with them. We just need to know the ratio of sodium to chlorine, or magnesium and chlorine, or calcium and carbonate, and calcium and nitrate and whatnot. We just need to know the ratio of ions to make this work. Now, there are polyatomic ions, all right? So polyatomic ions are actually, a polyatomic ion is a molecule that with a charge, all right? It's a molecule with a charge. Okay, and there's a couple of things. Like if I say carbonate, I expect you to know it's CO3 2 minus. If I say ammonium, I expect you to know it's NH4 plus. That's just part of chemistry, right? So if this is the only chemistry class you take, I do apologize, right? Because it's not like you're going to get a job interview. You're going to say, I need to know what ammonium is. I need to know what carbonate is. And you're like, got them, NH4 plus and CO3 2 minus. And they're going to be like, look, you're hired. I don't even look at your resume. Like, that doesn't happen. Okay, we know that doesn't happen. However, when you are doing chemistry, no matter if you're taking Chem 2 or further on, knowing the polyatomic ions is going to make your life easier because it's part of the language, right? Just like if you're playing soccer, there's terms that you use, right, that are different. If you're playing basketball, there's also basketball terms you use, right? In soccer, they'll use, make a run or up or behind. They use these things, give information to teammates. Basketball, you got pick left, pick right. You know what I mean? You wouldn't say pick right in a soccer game. Okay, same with football, right? Okay, there's different terms you use. Right? It's just part of the terms. Okay. Same thing here. That's just part of the terms. All right. So we need to know the names and the formulas of the polyatomic ions. Otherwise, this becomes very difficult. And again, naming and taking these names and making the chemical formulas to balance chemical equations, that's the fundamental foundation of chemistry. And so that's why it's so important. So when we talk about ionic compounds, we don't use prefixes now. Okay? And the reason we don't use prefixes is because the charges tell us how many we need to be because, right, they are neutral, right? They need to be neutral, right? They're neutral compounds, okay? What are the Roman numerals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And so 1 is, if you just do a vertical 1, that's fine. All right, a lot of times we'll just do that. So you can do it either way here. I'm sure you've seen some of these before. All right, again, either way you do it, I'm happy. Most of the time we'll use the right column, right, less writing. Okay, and the charge, the Roman numeral is the charge. So iron 2 plus means the 2 there. Iron 3 plus means there's a 3 there. I need to know the charge on the metal. Okay, that's very important. For example, let's say you went to the doctor and they said, oh, your iron's low. They don't just give you a bag of nails and say, hey, go have fun eating these, right? That's not what they do. You need a certain iron in your blood, right, in the hemoglobin. Well, what charge iron is it? It could be iron 0, iron metal, which is not. It could be iron 2 or it could be iron 3, right? And what you actually get is, I'm pretty sure it's ferrous, which is the Latin naming system that needs, still in use. We don't hardly cover it, but it's still in use. But it's ferrous sulfate, which is iron 2. And so you get iron 2 because your hemoglobin needs iron 2. Right? And that's very important. Okay? And so iron 3 is not what we want. Now, I'm sure the body can take iron 3 and make it iron 2, but why not just give the body iron 2? And I don't know. Maybe the body can. That's above me. All right? So let's do some examples of these compounds. Let's show you some examples. And this is important. My recommendation is do exactly how it's written here. All right? We're first, write out the ions and their charges. You got to have the charges here. You got to have the charges. Okay? Now, how do I know the charges? It's Greek. Why do I know sodium's +1? All right? And so if you remember the periodic table we covered, we remember group 1. Group 1, right? That's lithium, sodium, potassium, rubidium, cesium, francium, right? Group 1 is +1. Group 2, right? Beryllium, magnesium, calcium, strontium, barium, radium. Group 2 is +2 or 2+. Then you have scandium, silver, zinc, cadmium, aluminum. Scandium is 3+ or +3, silver's +1, 2+ or +2. Again, I'm writing them both ways because I don't care how you do it. I'm happy either way. Okay? Does not matter to me. If you write them plus 3 or 3 plus. Oh, I actually should do it both ways. So, right? Either way I'm happy with. Either way. Okay? Now, those are the only ones in our course that do not need a Roman numeral. Every other metal needs a Roman numeral. Right? But if I look at my periodic table, sodium's in group 1, I know it's plus 1. Chloride, anions, group 17. Right? Now, all the negative ones, they only usually have one option that's stable. So chloride will make a negative 1 charge. And so because we're plus 1 and minus 1, it's just 1 to 1. We're neutral. Sodium chloride, NaCl. Magnesium chloride, a little bit different. I got a 2 there and a 1 there. So a lot of times what we can do, make it simple, is cross charges. The 1 comes down, we don't write the 1. The 2 comes down, we write the 2. That's why it's MgCl2. Because now you have Mg, that ion, right? And you have 2 chlorides, and these are actually not to scale, but that's 2 plus. I have 2 minus 1 Cls, right? The Cl should be much bigger than the magnesium, but that's okay. All right, so now we are all together here. So we got a minus 2 and a plus 2. We're neutral. They have to be neutral. So crossing the charges works out. Again, here, tin 2, 2 plus, right? The 2 is 2 plus. Chloride, always Cl minus. Cross your charges. SN2, SN1, Cl2. Same thing here, tin 4. 4 plus, so tin is 4 plus. The 4 comes down, we don't write the 1. SN1, Cl4. That's very important, okay? All right, and so this gives us the charges in much balance. Again, more examples. All right, so magnesium bromide, MgBr2. Now, when we have polyatomic ions, in this case, I have potassium, plus 1, carbonate, minus 2, and so we cross the charges again, and I have K2CO3. All right, and since I have 1 carbonate, I just leave it as CO3. For aluminum sulfate, though, right, the 2 comes down and the 3 comes down. So the 2 is here for 2 aluminums, and I have parentheses around sulfate, 3 sulfates. Because if we took these parentheses out, what would happen? There would be no parentheses there. It would look like I have 43 oxygens. And we don't have 43 oxygens, right? I mean, what would that look like? Well, that would look like... Right? That would look funny, wouldn't it? Right? 43 oxygens. We don't want 43 oxygens. We want not 43 oxygens. And then magnesium phosphate, same thing. You have the 3 comes down, 3 magnesiums, the 2 comes over, you get the parentheses and the 2. All right. So hopefully that makes sense. Now, the next day of notes is all doing this, all right? And I'm going to recommend you actually try to do that without watching the video. And then watch the video as needed, if that makes sense. But I would try to do that first without watching the video because it's a worksheet just naming stuff and writing formulas down. All right, true or false? Are all compounds molecules? And this is fun. I just, for fun, in the day of this recording, went to both Google and ChatGPT 3.5, wherever the free one is for people. And I asked, true or false, are all compounds, or all, true or false, colon, all compounds are molecules? And it said true, both of them. All right, I thought that was pretty interesting. All right, because what's a molecule? How did we define what a molecule was? All right. Well, a molecule is a small, discrete unit of atoms bonded together. In fact, where are the molecules? Molecules, right? These are only non-metals, right? Above the stairs and H, right? So they're on the upper right side of the stairs, or the periodic table. Ionic compounds ionic compounds are a metal plus non-metal, right? Or two ions. Two polyatomic ions would be an ionic compound as well. So, ionic compounds are not molecules, right? So this is, of course, false. But however, your internet said it was true, right? Now, Chat GPT, I'll actually read it to you, kind of like I said, all compounds are molecules because, right? And it went into some explanation. I said, what about sodium chloride? Is that a compound? And it says, yes, sodium chloride is a compound. Then I said, is sodium chloride a molecule? And it said, no, it's not. I said, then how can all molecules be compounds? And it says, you're absolutely right to point out the distinction, and I should clarify my initial response. It was an oversimplification. And so it's false, all right? But that's just because you're using the internet to look up stuff, not always a good idea, okay? Are all elements molecules? That's also false. Are all molecules compounds? Ooh, what do you think? All right, well, no. What about O2, O3? Those are molecules. All right, so that's kind of fun. Up next, ionic compounds, hydrates. All right, think water is attached. Water is attached. Kind of like a magnet to something metal, right? Okay, if you have something magnetic that attaches, it's attached. It's there. It's part of the mass, but it's not chemically there, so to speak. Make sense? It didn't change the property, right? So, for example, if you have a tablet with a magnetic pencil, right? Great. Or if you have a magnet to a whiteboard, right? They're there. It changes the mass, but it does not change the properties of like the substance. It's not a chemical change per se. However, it's there. It's important. It changes the mass, so the molar mass is different, right? And it kind of works is when like these two on here, when they crystallize, these two copper compounds, water is in there, okay? It's not quote unquote wet, like feels wet. We call it wet because there's water there. Now, where I live in eastern North Carolina, southeast, it's a very humid environment. And so we can dehydrate these compounds. We can heat them and the waters leave. But where I live, the water, after it leaves, it comes back when it cools down because it's so humid. Even in the air conditioning, right? Okay, and so we just have, these hydrated compounds. And if you look, the name is the same for the ionic compound. You still have, all right, sulfate. Sulfate here is 2 minus, so that means copper has to be 2 plus, so hence the copper 2. The little dot here represents the hydrate, and since there's 5 of waters, right, it's penta and then hydrate. Same thing with copper 2 chloride, dihydrate, okay? So it's just, hydrates are pretty straightforward to name. The only thing that you have to remember is that when you're doing the molar mass, it's just not like it's copper's molar mass, sulfate's molar mass, and 5 waters. Or it's copper's molar mass, 2 chlorines, and 2 waters. All right? Not the last, we got 2 more. Acids. Acids, you got more and more H plus ions. Proton. Right? Think proton. Right? Because H plus is a proton. And there's 2 types, binary, HA, right? A for anything else, right? It could be Cl, it could be something bigger, doesn't matter, and HOY. Now, typically, it's written HYO. As you can look down to the screen, you can see it's HYO. But the reason I have it HOY is because when you actually bond it, H is bonded to O, bonded to Y. That's how the bonding works. The H's are always attached to the oxygen that are acids. Now, for binary acids, most of the time, they don't contain, some do, but most of the time they don't contain oxygen. So if there's no oxygen, you use hydro and ic. Okay? This is very similar to, like, when I was in Spanish class, learning how to conjugate verbs and whatnot. You know, same type of, similar, very, very similar. If you do have oxygen, right, you know, 8 becomes ic, and ite becomes us. That's the ending change. All right, so let's look at some of these. HCl, right? Well, that would be hydrogen chloride. If I wrote it out, right? You don't use the mono. Well, there is no oxygen, so hydrogen's gone. It becomes hydro, and then chloride goes to chloric, hydrochloric acid. That's how we name it. Okay. Same thing with bromide and iodide. Hydrobromic acid, hydrogen bromide, hydrobromic acid. Hydrogen iodide, hydroiodic acid. Now, if you look at these next four, I have sulfate, nitrate, perchlorate, and chlorate. Now, sulfate's a little bit different because we put the sulfuric in there, because sulfic is weird. So sulfuric acid. Then you got nitrate goes to nitric acid, because there's oxygen here, there's no hydro. Right? So the difference, we have no oxygen, hydro, oxygen, no hydros, right? So sulfate, sulfuric, nitrate, nitric, perchlorate to perchloric, chlorate to chloric. Here, this polyatomic ion, again, another reason to know your polyatomic ions, right? It's just part of the language. We have chlorite. So this is chlorite. So it's chlorous acid. Hypochlorite, hypochlorous acid. Nitrite, nitrous acid. Sulfite, sulfurous acid. Acetate, acetic acid. Cyanide, no oxygen, hydrocyanic acid. Right? No hydrogen sulfide, so it becomes hydrosulfuric acid. No oxygen, hydrogen fluoride, hydrofluoric acid. So that's the acid naming system. Right now, these ones right here that are in red on the right-hand side, these are our 7 strong acids in the course. Naturally, there are more than 7 strong acids. These are our 7 strong acids. If there's any other strong acids, I would tell you. Okay? Like I used HPF6. Right? I've used that acid, strong acid. Okay? We're not going to do that. I would tell you it's a strong acid. Okay? But these are the 7 strong acids. Now, when I say strong, it's not their gym performance. Like they can go bench press a lot. It's how they behave in water and what they do in water. Okay? And that's going to be important later on. Right? And the ones that are on the right-hand side of the screen, all right, not in the red box, are we call weak acids. These are weak acids. All right, and we'll cover that because strong and weak, that doesn't mean dangerous, less dangerous, more dangerous, faster, smaller, right? It's just their behavior in water, and we'll cover that later. But you can start to know the 7 strong acids. And it's the middle 3 halogens. Right, so not fluorine, not AT, but ClBrI, right? And then there's 4 polyatomic ions, sulfate, nitrate, perchlorate, and chlorate. Those are your 7 strong acids. Now, last thing your book talks about, organic compounds. And it covers it, introduces it, all right? Hydrocarbons contain only C and H, carbon, hydrogen, right? And alkanes here, these are all what we call single bonds. Wow. All right. And so, again, this is not a big part of the class, but not meth, the drug, but metha is 1. Etha is 2. Propa is 3. Buta is 4. Penta is 5. You can probably see the pattern here, right? And so you see it's the number of carbons. The number of carbons. And I want to highlight. Number of carbons here, right? Number of carbons. So that tells us the number of carbons. And the number of hydrogens is determined as after we do the bonding chapter. That's pretty straightforward how to do that. Okay, so those are your simple alkanes up to 10. Can you get more? Yes, of course. All right, now there's something called functional groups, and as they're appropriately named, they determine the function of the molecule. Alcohol. Now, the alcohol, this has to be like a carbon or something. It cannot be a metal. Right? That cannot be a metal. Like sodium with OH, not an alcohol. Okay, aldehyde, and just so you know, it's C double bond O double bond H. Carboxylic acid, C double bond O, another O, and then an H. So those are 4 functional groups that you may have heard of, right? Like amino acids. These are the amines. These are the acids, right? And so, just introducing that to you, and hopefully that works. But again, the naming, do the next, like day 17, do day 17 without following along in the video, right? And then do the video to make sure that you understand the explanation if you need to, right? Okay? And make sure your answers are right because it's a fundamental. Hopefully, I know that's a lot of information. Hopefully that makes sense. And let me know if you have any questions. We'll see you next time, guys. Take care.